Good morning, everyone. So, in mostly, if I assume that this course is mostly for the MTech student as a core course, so I can assume that you have done already your bachelor degree courses. So, in bachelor degree, you may have encountered the structural analysis. So, in the structural analysis, you have seen how a structure should be analyzed due to certain type of static forces. So once the forces are applicable on the structure, we have seen how to perform that analysis. But but in that course, we will extend our knowledge from the static to dynamics, and we will try to see how the response of the structure will be performed once it is subjected to some sort of dynamic excitations. So there are several type of dynamic excitations are involved into it. So for example, structural study of how the structure respond to the load that vary with time. It includes a range of topics including the analysis of vibration, impact of dynamic forces on structure, and the ways in which the structure absorbs or dissipates the energy. That we will also able to see, like once we are discussing that how the energy means how the structure is responding, then we will also able to see how we can able to mitigate the responses as well, so, or control the response. So next thing, suppose if I see the applications of this type of this structural dynamics course, so we can primarily see in these four broad spectrum the course can be very well applicable. First, civil engineering. Most of you are from civil engineering. So ensuring the stability and comfort of the structure subjected to the dynamic loads, for example, earthquake, traffic, wind, human activity, or several types of other loads can also be into there. Then the seismic engineering, that is mostly due to the earthquake. Then aerospace industry. So like once the once the people are making the aerospace structure, so it can be some structure also, it can be aircraft as well, or anything can be possible. So in those cases, the analysis of vibration is also one of the very crucial aspect of it. Then if you see in the mechanical engineering also, like for example, some type of machines are vibrating, or some rotors, some dynamo, or something. So all those things are coming in the form of the structural, in the structural dynamics. All those things are coming, and there is also sometimes it's very well resembles with the theory of vibrations as well. So sometimes this course is also known as the theory of vibration. There is a very good overlap with the theory of vibration and the structural dynamics, because in theory of vibration, like if you see single degree freedom system, multi degree freedom system, continuous system, numerical integration, all are also part of the theory of vibration as well. Uh, yeah, so but in structural dynamics, we will also see some aspect of the earthquake engineering which is generally not that much covered in case of the theory of vibration. Like for example, response spectrum and all other things, we will also look into it, which are generally not there in case of the theory of vibration. Okay. So before we go there, so maybe I would like to show some videos. So you can see the left one is the video of a Tacoma Narrow Bridge. So you can see that how the bridge is vigorously vibrating due to the wind load. And you see that it finally get collapsed. So this is one of the prime motivation or the thrust factor from where the structural dynamics courses comes into picture. So if I just tell some history of that, Tacoma Narrow Bridge was designed for almost 3 to 4 times more wind load. But due to the but in the small wind speed also, the structure get collapsed because it reached to the resonance. And you can see so vigorous vibration happened. It's a real life video. It's not anything like added or maybe AI generated. No, it's not like that. It's a real life failure video. So you can see that like you designed a bridge, but due to the wind of much less wind speed, the complete collapse occurred. So it's a very serious event. Then I'm going to the next one. So you can see that the earthquake, like a vibration of the structure. So you can see how the structures are getting collapsed due to earthquake. Recently, the Turkey earthquake, which gives a very fresh reminder for the need of the structural vibration, means the structural dynamics, that if we are not considering it, what type of catastrophe it can lead to. Previously to that, Nepal earthquake also has a very huge devastation in that sense. Then if we see, like some type of machines are vibrating, so we can see that. And also sometime, like suppose if some vehicle is moving, or means suppose train is moving on the bridge, we can feel the vibration that yes, something passed, and we can feel that. Suppose if you are also standing on the bridge and some vehicles like a big truck or something is moving, you can still feel the vibration that yes, something is vibrating. So in all those cases, if you see, to measure the vibration, to understand that how much vibration is occurring in the structure, and also if you try to control that vibration, all those cases, these structural dynamics course like act as some sort of skeleton for that whole thing. Okay. Oh, also you can see that like nowadays with the renewable energy, we can see that sometimes these tower type structures are made, and they are also subjected to the very significant amount of vibration in that sense. And also once we are working with the sound, that also primarily generated due to the vibration of the wall or the panels. So that also create a structural dynamics problem. So here you can see that once they are tuning it, so it gives a oscillation. Okay, so all those things will be covered, a structure which is subjected to this type of forces. So once we are talking that how we are going to analyze, that means we are in our mind, we have like a structure, so which is primarily a physical structure. So it may be a building, it may be bridge, or it may be any of the form what we have seen, or which are not seen also but has some sort of dynamic responses. Because you see, like we just saw some of the cases, not the entire set. So the structure, and then the structure need to have some type of mathematical model. Because like suppose once I talked about a bridge, the bridge is a big structure. So once we are solving it, we are solving for some specific output of it, that what we are going to look from that bridge. So in that case, what are those outputs we are talking about? That we have to be clear in our mind. Is it in terms of acceleration? Is it in terms of displacement? Or it is in terms of bending moment, shear force? What type of parameters we are looking for? That should be clear in our mind. So what type of parameter? What is our output? Parameters, like for example, it can be acceleration, it can be displacement, it can be bending moment, shear force, any of that thing, or something, anything more or something. So to find out that, we need a mathematical model. So we need a, and once we are talking that we need a mathematical model, that involves how we are approximating our original structure into a mathematics. So there is a two things. So here we are having some sort of approximation and some assumptions are also there, and those are also leads to what type of output we are looking for, and what is also the fidelity of that thing, like how well we are going to capture it. Suppose for example, you have a bridge type structure and you want to see the bending moment at each point. So you will try to capture, so your mathematical model should able to capture at these points so that it can gives you the output accordingly. Or maybe you just need that, okay, just tell me what is the deflection at the midpoint. Then you can make your model accordingly. So obviously there is a trade-off. If you are having much detailed model, it will be computationally more challenging. Or if you are having a model which is much simpler, then it will be computationally faster, but you will get less result out of it. That is always the true case, because you cannot have both the things. Okay. So in this case, how we are making that mathematical model is what I have shown at the very beginning, that we will study the systems into the three different forms primarily: SDOF, MDOF, and continuous system. Okay. So in single degree freedom system, like, we try to capture the full thing using just a single degree freedom system. In the multi-degree freedom system, we will try to capture the full thing with several degree of freedoms. Whereas in case of the continuous system, we will try to capture the full thing in a continuous manner, so that everything will be captured very clearly. Obviously, the complexity is increased. So they are increasing complexity, more complex. So once we are going down, the MDOF system is more complex compared to the SDOF system, and continuous system is much more complex compared to that. Okay, so obviously we should start with the simplest thing. So now let's see how a single degree freedom system is occurring and what is basically a single degree freedom system. Before we start that, do you have any question up to this stage? No question? Okay, so we can go ahead with the next one. So please feel free, if you have any question, please raise your hand and you can ask the question. Okay. So now let's see what is a single degree freedom system. So single degree freedom system is generally, like, if you think, we have, like, just let's assume the problem of a water tank, inch water tank. I think most of you have seen a inch overhead water tank. So that's a heavy structure in the overhead which contains the fluid mostly, and that structure is supported by some piers. So if we try to see that structure, what we can see, that there is a heavy mass at the top. Okay, so that mass is the mass of the concrete also, and also it contains the fluid, so that fluid also will be there. Sorry. So both the things are there. Now after that we will have the columns. So columns will primarily provide the stiffness. So that will be stiffness in terms of columns. Okay. So this system can be, so now this system can be subjected to wind or it can be subjected to earthquake. These two are the two prime structural dynamics force we can think on a inch water tank. So suppose if it is subjected to ground motion, or maybe it is subjected to some sort of wind load on that. So how we can able to analyze this structure? So you can see, we can draw this, we can analyze the structure like this way. We may think that mass is condensed here, M mass, and this pier system is gives the stiffness. So that will have a stiffness component here. Okay. So now, so this is the simple single degree freedom representation of a water tank structure. Okay. We can also think for a bridge, also the very similar thing can be possible. Like, for example, you have a, like, these are mostly, like, suppose you can think like a piers. So in that case, if you see that these are, so these can give the mass and this can give the stiffness. That way also we can able to start thinking the bridge problem, that how we can able to do that. Okay, so yeah, so now if we see that we have this mathematical model. Okay, any question up to the construction of the mathematical model from a real structure? Please, if you have any question, please feel free. Okay, no question. Very good. So now what we can see, that if we are now displacing, maybe I will just erase that part. So now if I am displacing that part, and suppose now we are thinking that the structure is deflected by some amount. Okay, so let's assume this is deflected by x amount. Okay, so what will happen? We have deflected by x amount. Now it will have some sort of inertial force, backward direction, and also some type of restoring force due to spring action in the backward direction. And maybe you have applied some force on that structure, that is a force. And also often there is some damping also present in that structure, that is C. Damping means you can think that once the structure is trying to vibrate, there will be some air. So once it is going and coming back, it is displacing some airs, and therefore it has a high amount of friction generating. So it dissipates the energy due to that process. Okay, so that Cx dot is also another force going in the opposite direction. So if I going to do the force balance in this mass, so what can I do? Summation of Fx equal to 0. So I can write it mx double dot plus Cx dot plus Kx, that will be equal to force. That how much force we have applied, that should be equal to mx double dot plus Cx dot plus Kx, that is equal to the force. Any doubt up to this stage? No doubt. Very good. So now for a single degree freedom, so now first we are talking about a undamped SDOF free vibration. So in that case, what happened? It's an undamped system. That means first we will assume that C will be equal to 0. So that means that there is no damping in the structure. So and there will be no force as well, because it's a free vibration. We will let the structure to freely oscillate. So we will have mx double dot plus Kx, that will be equal to 0. Any doubt up to this stage? Very good. Here, remember one thing, once I am writing that double dot, that means this is the second order derivative, and once I write x dot, that is dx over dt. Okay, so this is so first one is the first order derivative, which is representing the velocity. Okay, and then next one is the second order derivative with respect to time, which represents the acceleration. Okay, so we are having a mass times acceleration plus stiffness times displacement should be equal to 0. After this stage, no question.
Sir, in this both the equations we are always in elastic range, like we are not going into nonlinear range.
For this course content, we are not going into the nonlinear case. There is also, after that, there is also one type of courses are there, that is the nonlinear dynamics, where the stiffness is no longer like a linear. So then that stiffness can also be altered. So there we can able to have the nonlinear. Okay.
So means it will cover mostly the cases which we encounter in real life.
Yeah, because most of the cases, if you see, like once we are going to calculate the natural frequency or try to understand the vibration, we try to restrict ourselves in the elastic range, and majorly, like like I can say like 99% cases, the vibrations are in the linear range. Very few case it is going to the nonlinear range. Why I am telling? Because if you see like a machine vibration problem or some problem like where the vibration is very continuous in nature, there nobody want to go for the nonlinear range that much. Maybe it go smaller range, but not in a very high amount of nonlinearity, because then what will happen? Stiffness degradation will be very fast. It may lead to the fatigue and all those type of problem as well. So people do not go into that high level of nonlinearity. Okay, but yeah, some problem definitely people designed it for the nonlinearity to be occurred, but these are very sophisticated type of thing, and
because
that is not also the part of this course. Okay,
so for earthquake problem, we always go into the
we
the structure
always going to
behave
have that
non-linear.
nonlinearity problem. Exactly, I do agree with your point, but that is like once we are having like a high like a vibration, and that also you can see we are not going to calculate the natural frequency for that nonlinear type of problem, because natural frequency and all those things are not that well defined there. There is some techniques like using the harmonic balance and all those things, you can able to calculate those things, the natural frequencies for the nonlinear systems as well. But in normal cases we are not calculating the natural frequencies there. And also in the earthquake it reaches for very few cycles in the nonlinear range. Okay, but yeah, once it goes to the nonlinear range, yes, definitely it starts staying in that nonlinear. Okay,
Thank you, sir.
thank you. Okay, so thank you very much for asking the questions. And yeah, so suppose now we have this equation of motion, and let's try to see how we can able to solve it. So first of all, once we have a differential equation, we should try to understand what type of equation is it. So can anybody tell what is this equation?
Homogeneous equation. So homogeneous equation.
Homogeneous equation. Okay, so first point is that
Second order
homogeneous.
homogeneous.
Perfect. Anything else?
Single degree.
Second order. Very good. It's a second order equation as well. Okay. Anything else? Huh? Linear. Okay. Linear. Very good. Anything else?
Single degree.
More or less it's all right. Like, so we can say that it is second order linear ordinary differential equation. Why it is ordinary? Because all the 3 points were told from the class. Just 1 point I added, that is the ordinary. So why it is ordinary?
So no higher order.
Huh?
No higher order terms.
No, we have a higher order. That means it is second order.
Means power terms.
Yes, it is a function of time only.
Time.
It is,
yes.
if it is function of 2 or more parameters, then it will become a partial differential equation. So here it is a function of time only. So that's why it is ordinary differential equation. Make sense? Very good. Very nice. So it's a second order ordinary linear homogeneous equation. Why it is homogeneous, by the way?
So we don't have any.
Yeah, it is equating to zero. There is no constant term present into it. Okay. So now if we start thinking that okay, how, and also another very important point, it's a constant coefficient, because all the coefficient of the x dot, x double dot, all of the things are constant. They are not changing with time. Okay, so it's a constant coefficient as well. So I can also write it constant coefficient. There are some type of structural dynamics problem associated to the like satellite launching and some of the cases where mass matrix becomes sometime the time dependent. Like suppose some rocket is going, it is like utilizing its fuel, so the mass is actually reducing with the time, or maybe something the rocket is, some mass is get ejected, so then that mass is get separated after a certain time. So those cases will be different. They are not constant coefficient problem, but here the thing is constant coefficient. So now if a differential equation, like if a ordinary differential equation is constant coefficient, so how we can able to write? So we can assume the solution x as a into e to the power of lambda t. That is a very standard way to assume the solution of a ordinary differential equation with constant coefficients. Agreed? Now if I assume this, what will be x dot? Lambda times a e to the power of lambda t. What will be x double dot? Lambda square a e to the power of lambda t. Very simple. No doubt, I think. Perfect. Okay. If there is no doubt, I can just try to substitute. So that is my equation 1. This is my equation 2. This is my assumed solution 3, 4, 5. So now I am substituting. So now substituting equation 5 and 3 into 2. Okay, I am substituting equation 5 and 3 into equation number 2. So what can I get? M lambda square e to the power of lambda t into a plus k into e to the power of lambda t into a, that is equal to 0. All of you agree with me? So if I try to condense this equation, what can I write? I can write m lambda square plus k into a into e to the power of lambda t should be equal to 0. So it has three type of solution. One case, either e to the power of lambda t equal to 0 or a equal to 0 or m lambda square plus k is equal to 0. But if we think that if we are saying that a equal to 0 or e to the power of lambda t equal to 0, that means we are having a trivial solution of x, because they are nothing but the displacement field what you have assumed. Okay, so x equal to a into e to the power of lambda t you have assumed, and now you cannot say that a or e to the power of lambda t is becoming 0. That means your x is itself become 0. Okay, so you are then solving a trivial solution. That's not allowed. So obviously we can understand the one and only option remained, that is m lambda square plus k, that is equal to 0. Okay, so this thing is telling lambda square should be equal to minus k by m, or this tells lambda will be equal to plus minus I root over of k by m. Make sense? Straightforward mathematics I just did. Good. So once this is the case, and now let me assume that k by m equal to omega square. Okay, just I assume some parameter. Okay, let's not call what is omega or anything. Then let's just assume that omega square, just to make our life simple. So what will happen? Root over of k by m will be equal to omega. So I can write lambda will be equal to plus minus I times omega. Can I write that? I think, yeah, I can able to write it. So if I am able to write that, so I can write now, so that it becomes my equation number 6. So now if I just substitute equation 6 into equation 3, what can I get? X equal to a into e to the power a1 into e to the power of I omega t plus a2 e to the power of minus I omega t. Because we are having two solutions of lambda, so obviously we have to use that two solutions. Agreed? And how we can able to use that two solutions? So we have to assume that, okay, one solution is with e to the power of I omega t, and another solution will be e to the power of minus I omega t. Both the thing with some sort of coefficient we are multiplying, and we will get that solution. Agreed, all of you? Any doubt? up to this stage? Good. Once we go up to this stage, now the next thing comes. Okay, so now here tell me, what are the unknowns? What are the parameters known to us and what are the parameters unknown to us? A1, A2 are unknown. Do you know omega, by the way?
Yes.
Yes, because omega is this, and K is known for the system and M is also known for the system. So omega is known to us. Okay. What about T?
Variable.
T is the time. So that is the variable. So it will vary. So definitely once we are plotting that, we will know what is the T and how it is varying. That is known to us. I is root over of -1. That is also known. I is root over of -1. That is also known to us. And E is exponential. That is also known. So all the things are known except A1 and A2. So now what is our task? To calculate A1 and A2. Perfect. So let's try to do that. Maybe I'll go to the next slide. So what form we got? So we got A1 e to the power of I omega t plus A2 e to the power of minus I omega t. That we got from the last case. Do you remember the Euler's equation?
Yes.
Euler equation was e to the power of I theta, that will be equal to cos theta plus I sin theta. Okay, and e to the power of minus I theta should be equal to, so automatically e to the power minus I theta equal to
Cos theta minus I sin.
Just okay, let me do it properly. So that will be cos of minus theta plus I sin of minus theta. That means cos theta minus I sin theta. Okay. So if this is the case, so that is the Euler's equation. Okay. So now if I use the Euler's equation here, what can I get? That will be cos of omega t plus I sin omega t plus A2 into cos of omega t minus I sin omega t. Now what I am doing, I am trying to put both the things together. So A1 plus A2 into cos omega t plus I into A1 minus A2 into sin omega t. That is my x. Can I say that? And I am just reassigning it as C1 into cos omega t plus C2 into sin omega t. Can I do that? I had two unknown A1, A2. From there, I changed the I used the Euler's equation and I changed it from e to the power of omega t to e to the power to the trigonometric identity, and I am just expressing it in terms of C1 and C2. So we had previously two unknown and now also two unknown. Instead of A1, A2, now we have C1, C2. Okay, but the good point is that you may feel little better or maybe little comfortable because you are not dealing with the imaginary numbers. Now you can see in the first equation here you have imaginary numbers e to the power of I omega t, e to the power of minus I omega t, but now here you are having only cos omega t and sin omega t. So the imaginary part is not there. So that may be some sort of like a relaxing thing. Although it's not anything big deal, but it's okay. So we have this one. Okay. Now our goal is to calculate A1, A2 or C1, C2. Whatever I can say. How should we do that? Do we have any other equations?
Boundary condition.
Boundary conditions. Okay, that's the interesting point. Anything else except boundary condition? initial conditions. Okay, good. There are two things we heard: initial condition and boundary conditions. Okay, maybe I just write it down. So first we had boundary conditions. So I first put boundary conditions, and secondly we had initial condition. Okay. Any other thing except these two? Okay. If there is also no other things, okay, fine. If there is other thing also, that is also fine. Let's discuss with these two first. So suppose in context of a differential equation, these two terms are often used, and most of the cases people also get confused with these two terms. What are they actually? So suppose if you have a differential equation as a function of space and time, that means you have a function something like x comma t. Here you do not have x comma t function. Here that x itself is the function. So here we have only f of t. We do not have f of x comma t. No. Once we are dealing with a continuous system, then this thing happens. F of x comma t or f of x comma y comma t. Like suppose if we are solving a plate problem, we will have f of x comma y comma t. If we are solving like a 3D problem, then we may have f of x comma y comma z comma t. That full space will come into picture. But here once we are solving a single degree freedom system, or we will solve the multi-degree freedom system, we are ignoring the space. We are thinking that space are some sort of lumped into the lumped masses. Okay, and we are solving that full thing. So in those cases, how the boundaries, that means suppose if this is the case of a partial differential equation or some variable, if I am giving something here or something like this, means I am specifying some locations in the space and telling that how it is varying with the time. They are known as the boundary conditions. Make sense? For giving a much better clarity, maybe I can take an example of a beam. Like for example, you have a beam like this. Now you are saying that this location, like let's say you put a hinge. So you are saying that this location will not going to vibrate. That means you are writing that your W may be your deflection of the field. So you are writing W of x comma t. Sorry, this is W of x comma t. So you are saying that this is always equal to 0. So this becomes your boundary condition, because it is telling in the space particular location how it is varying with the time. Make sense? Any doubt with what is the boundary condition?
Yes.
Now if we come to the initial condition, initial condition is something like we are writing this. So we are specifying a configuration which at t equal to 0, how it looks like. That is known as initial condition. Makes sense? So initial condition is defined in terms of time, and boundary condition is primarily defined in terms of space. So boundary condition cannot come here because we do not have space. We have only time, so it is initial condition. Makes sense, I think. And thank you very much for putting that two name, so we can have that discussion. Okay. So it's an initial condition. Now, initial condition of what? Don't forget, we were solving this system. We had a mass, we have a stiffness, and we displace it at some point and we let it go. For example, if you think, like let's say we have this is our structure maybe. Now at initially I just bend it at some point and I let it go. So you can see that the oscillations happens. Okay. Now you may leave it with some initial force as well or initial velocity as well. So there are the two possibility can be associated with this. One, that at t equal to 0, so at t equal to 0, you may have two cases. One is x of 0 and x dot 0. Means you may have given some initial displacement or you may have given some initial velocity in that two thing. Okay, so whatever you have given, you can get it. So let's say we have given this x0 and this is x dot. So what can I say? So this equation, so sorry, just previously let me check what is the number going here. 6 and this becomes 7. So this is my equation number 7. This is my equation number 8. Okay, this is equation 9. This is equation 10. So if I see that x, so if I just substitute, x0 will be equal to c1 cos omega 0 plus c2 sin omega 0. That means cos omega 0 is 1 and sin omega 0 is 0. So that means this is only c1. So we can say that c1 will be equal to x0. Can I say that? No, simple, not a big deal. 11 number. And also importantly, if I just substitute that 11 into 8, I can write what? X equal to x0 cos omega t plus c2 sin omega t. Now what will be my x dot? X dot will be this into omega sin omega t with a minus sign plus omega c2 cos omega t. Okay, now at 0, at t equal to 0, x dot 0 will be equal to omega c2 it will be omega c2. So c2 will be equal to x dot 0 divided by omega. So my total form of x of t should be equal to x0 cos omega t plus x dot 0 omega sin omega t. So that will be my total form. So this will tell how the t point is going to oscillate over time. If we are assuming that initial conditions are known to us, there is nothing unknown, no unknown. All the things are known. If we think that this is known, that means this is known, omega is known, t is also known, cos, sin are the functions, and plus is also function. So all those things are known to us. So we can able to get a complete response of the structure. Agreed or not? Okay. So how the function looks like?
Sinusoidal.
Sinusoidal. Okay. Because obviously it is summation of the cosine and the sine. Cosine and sine are similar, just having the, what is the difference between these two? Phase difference, exactly. So they are only the 90-degree phase difference. Otherwise, both of them looks exactly same. Just they are 90-degree shifted. That's all. So obviously, if we are adding these two with some sort of linear, like what to say, that linear interpolation, they will remain sinusoidal. There is also no doubt on that thing. So we can write a small MATLAB code for that thing, and we can try to see that how this type of vibration can be seen. So you can see that we have this MATLAB script. First the MATLAB script comes, that is the CLC. CLC is just to clear all the variable, and then also there is a clear comment, okay, noise. Then we are having the parameters. So first, like, we are inputting the, so once it is started, so then there will be input. So it will ask the input for to input the stiffness, which will be in the Newton per meter. Then input for mass, that will be in kg. Then input for initial displacement, and input for the initial velocity. Okay. Then you can see that natural frequency is root over of k by n, what we have assumed as the omega n. Then we are giving some t equal to 2 pi in pi omega n. Okay, that will be your vector. Then it is up to this line space subplot. So here you can see that the calculation what we have done just is written here. X0 into cos omega t plus V0 divided by omega n into sin omega t, and V equal to, you just do a differentiation of it. So you are doing a differentiation so that cos, that omega n is coming here, cos becomes sin, and sin get changed. And here it is V0 by omega n, so omega n and omega n which will come, that they will be cancelled out. So V0 into cos of omega n into this. So that's good. You can see also how we can write that. Then we are coming into the figure. Then subplot. Subplot, you can see what is meaning of subplot. Don't worry. And it goes like this. So let's see. So let me just enter here. So stiffness, how much? Please tell. Please.
20,000 kilometer.
Huh?
20,000 Newton meter.
20,000.
Newton per meter.
20,000. Okay. 20,000. Okay. Then.
So we have to enter in kilonewton, bro.
No, that is in the kg.
Okay. Kg.
Enter the mass. Mass. How much mass should I put?
500 kg.
500 kg. Okay. Good. Then initial displacement in meter. Maybe 0.1.
0.1. 0.1 is too much. 0.1.
Okay, nice. Here it is. Point maybe. Here also put it 0.1. Now let's see. So you can see that this graph is plotting, and you can see a very nice displacement graph and velocity graph. How much displacement we have given? 0.1
meter.
Velocity we have also given 0.1. We can see that both have started from 0.1. Okay, both of them are not going, the maximum is not going all the cases 0.1. They are varying. Okay, and there you will find, see a interesting spiral plot. Did you see that before? Maybe these two plots are okay, we can easily understand. But did you see that plot, the third one?
Yes.
Okay. The third one, let me first see what are the axes of that plot.
Time, displacement, and velocity.
So if you see the first plot, it has a axis here, time. X-axis is time, and second and y-axis is displacement. If you see the other one, that is time versus velocity. Okay, but here we are plotting both displacement and time with displacement and velocity with time. So we can see that a complete spiraling things are there. Okay, so if we see this plot from this axis, this side, can you see my cursor here? If you see it from this side, we can able to see this plot, velocity versus time plot. And if we are seeing it from top, then we can see that first plot, displacement versus time. So this is a, and another question automatically comes into picture. We have C from x-axis, we have C from z-axis. If we see from y-axis,
displacement versus velocity,
then we can see displacement versus velocity and how they should look like. Anybody please? Circle, exactly, or ellipse. It will be ellipse actually. Circle is a special form of that, but we will generally get it a ellipse. So in that side, means once we are looking it from the displacement velocity side, that is known as the phase portrait. There we can able to see that how the graph is started and how it is curved. And this graph will look fantastic once we will do for the damped vibration, because now it is going straight all over, that it is not dissipating its energy. Now once it will start dissipating its energy, then you can see that it will spiraling to the center. So it is like having a big one and then it is getting spiraled down. Okay. So any question up to that? Any question?
Sir, the displacement is velocity. We are means the maximum amplitude is more than 0.1. What we have given in the initial as an initial velocity, but for displacement it is almost 0.1 or 0.1 only. Or
No,
means
it is
we are not able
look,
to see.
in the velocity it starts from 0.1, go down and again go up.
So displacement for displacement.
Yeah, displacement it was 0.1. So how much we have given?
We have given 0.1.
Yeah, we can also change the value and we can try another. Okay, we can try it once more, not a problem. Yeah, so tell some value. Please, no issue.
1. Stiffness.
How much you have given?
20,000 we have given.
20,000. Okay. Then this one, 100. This one maybe. This time we will put different.
7.
Maybe
0.050.
0.50. And this one maybe we will put it, how much? Minus 0.2. Okay. Let's see how it. I'm back. Very 20. So again you see it starts from here 0.5, 0.05 displacement, and velocity you see starts from, we have given minus 0.02, it starts from there and go like this. Here one point I would like to mention, omega n is quite high value. Therefore what happened, displacement is mostly dependent on x0, not on v0, because v0 divided by omega n is there. So therefore it actually diminishing that term. So maybe we can try with one more where omega n is less. So we will put k and m more or less similar, so that omega n will be somewhat like 1. And then let's see. Then we can see that in displacement also it will be no longer remain near 0.5, 0.05. It will be changed at somewhere. Let's try with that. Okay, so here like let's say we have given it 100. Mass is also we give 100. So omega n should be 1. Okay, now give this one, maybe I give 0.05. and this one minus 0.2. Okay, now let's see. So previously we have seen whatever the displacement x0 we were giving, it was mostly in that same range. It is not getting changed much.
Magnification.
But now you see we have given 0.05 for the displacement. But now if you see, it's already go up to 0.2 because that velocity contribution is now significant. Previously it was get divided by 100 times because omega n was more or less 100 in that case. But now omega n is become 1. So now x0 and v0 both have the significant role to play in that. Okay, so we will have this way, and now you can see both of them are more or less coming like that, because there we have given 0.02 displaced velocity, but still you can see that it goes little bit up because there is some portion of the displacement is also affecting that. But here displacement is get divided by omega n, means multiplied by omega n. So therefore that effect is less. But previously that effect was quite significant. Because we have seen that velocity one is getting increased, but displacement was not get changed. But now you can see that velocity get more or less similar, but displacement get changed. So these all those things you can play with that, and you can start understanding that how those things are.